2. So we continue with chapter number 11, part 2. So the protein, they can be ionized. Okay. So for example, this ionizable amino acid such as glutamic acid and arginine, part of the polymer chain of protein, can uh, can be ionized. Okay, when one of their side chain are ionized, so the total charge of the protein chain and electrostatic interaction after the ionization energy of the other amino acid side chain. Okay, so if these are in plus or minus, so it will change this ionization energy. Okay, so ionizing one side chain makes it harder to ionize other, and this spread out a protein hydrogen curve over a wider pH range than it is if the same group are integrated in a solution. Okay, so this one is from our chemistry. Okay, so if one side chain already ionized, so it is harder to other side chain to be ionized. Okay, so but this effect can be reduced by the addition of NaCl salt, because salt screen the electrostatic interaction between the charge on the protein. Okay, so meaning that if these are already ionized, so this side chain will not feel uh, this electrostatic interaction of this side chain. So it can also be ionized. Okay, so the free energy chain for ionizing one particular group on a protein will change in value from D to D plus 1. So let's say Na plus or Na C2 plus, C2 plus, or this 2 plus is equal to this free heat energy minus RT ln K naught plus WD plus 1 squared minus WD squared. So where K naught is intrinsic equilibrium constant for the group in the absence of electrostatic interaction. So it can be A and B. Okay. So this equation is the change in the electrostatic energy. So W is equal to this equation 1 over 2 water epsilon over 1 plus over lambda D plus A. Okay, so we can get this energy change when the protein is ionized. Okay, so to know this, we can again with in our chemistry. So we have titration. So protein titration, consider ionization equilibrium in which the charge increased by 1. And P, the permanent charge, will be ionized in the pH range of interest, and N, ionizable charge. So let's say the protein has 4 part that it can be ionized. So we have N equal to 4. So the free energy change, the number of ionized charge increased from I to I plus 1 equal to this equation. Okay. So we have the two, so we can just put N minus I. So we have N, let's say 4, the first side chain, the second side chain, the third side chain. So this one is for the third side chain. So we can calculate the free energy chain contributed by that side chain. Okay, so where N minus 1 minus I over I is the side, the forward and reverse ionization process that can. Okay, taking the equilibrium constant of ionizing charge is plus AI plus 1 K naught exponential minus this equation. So where AI is the protein with ionization state I. Okay, so 1 state, 2 state, So taking the log or the ln of this equation, so we can have the pH minus log A minus 1 I plus 1 AI equal to PK plus so with this we have this equation. Okay, so we can calculate the pH using this equation, or when half of the group have been ionized. Okay, so when half of the group, so let's say we have the same protein 100, so if 150 already ionized, okay, so we have this equation. Okay, so using this we can get this the pH can be calculated using this equation. So where alpha equal to A minus AH space A minus. Okay. Okay, so from this protein saturation experiment, so we can vary the pH and measure the alpha. Okay, so a plot of pH minus log versus minus log alpha 1 minus alpha versus alpha. Okay, so we are going to get a linear slope. Okay, and the slope can be used to calculate the that electrostatic, the change in the electrostatic energy. Okay, so here this for that we can know how many, for example, this one is how many sites in the protein, or how many side chain in the protein that can be ionized. Okay, so contohnya 5, 5, 6, 7, 8. Okay, so we know, so we can imagine without knowing the structure of the protein, so we can estimate or determine, let's say, how many glutamate that it has, how many glycine that it has, and how many arginine that it has. Okay, in that long polymer of protein. Okay, so next is the membrane. Okay, so membrane. So when we have a membrane, so the membrane also consists of a protein and a lipid bilayer. Okay, so that lipid bilayer also have a side chain. Okay, that side chain can also produce a charge. Okay, okay, so here, so you can see that bilateral membrane usually have some charge at their surface arise from the polar head group of phospholipid, charged amino acid on membrane protein, charged sugar on membrane glycoprotein. Okay, so here we have. So if this membrane consists of this phospholipid, protein, and glycoprotein, so it will produce the charge. Okay, so the membrane surface will influence the distribution of dissolved charge. Okay, so if we have the dissolved charge, the dissolved ion, so the ion will be attracted to this charge at the bilateral membrane. Okay, so if it has some attraction to this bilateral membrane, so the number of ions in the solution will be less. Okay, so taking the Poisson equation and the Poisson-Boltzmann for membrane, okay, and taking 1D Poisson-Boltzmann, okay, 11.36 from our textbook, okay, so using this NaCl, G plus minus 1, okay, so solving it, we can get this equation, okay, and again, so solving this equation, so we're going to get this equation, or this one is just the integration of this equation, so we're going to get this equation. Okay, so the surface charge density, so at the membrane surface, so how how many charge that it has. So we can calculate using this equation. So sigma equal to minus var epsilon 45 d var p not over d x. Okay, so we can calculate using this equation for the surface charge density. So how many charge in that membrane. So at x equal to 0 and equation 11.40, so we have get this surface charge density sigma equal to this equation. Okay, so and for surface potential var p naught, okay, so equal to square root of c over 136. Okay, or you can see that we use this equation, or if we linearize this one using the Taylor expansion, linearize it. So when we solve this equation, so we're going to get sigma equal to var epsilon over 4 5 lambda d var p naught. Okay, so the charge density of the membrane can be calculated using this equation. Okay, so the 11.38, so you can see that the charge potential, okay, the total potential for that membrane is equal to this equation minus x lambda d, the initial electrical potential. Okay, so this one is kalau contohnya kalau kita ada satu tanah, okay, so if we can have 4 lot, okay, so kalau semua lot dah diisi, okay, so that we get electrical potential for that level. Okay, so at low ionic strength, as the salt is diluted, some ion must remain near the membrane to maintain electronegativity. Okay, so ion attached to the membrane. As a result, the concentration right at the surface goes to non-zero limit at the above concentration is reduced. Okay, so this one you can see that most of the ions are in at the membrane. The ion in the solution is reduced. Okay, so the 11.38 can be simplified as this equation. These are the again the surface charge density can be calculated using this equation. So the concentration 2 kg by naught. So Kx. So the concentration at the membrane surface is equal to this equation. So this one. So simplify this. So we're going to get this equation. Okay, so what we can say that the concentration of naught is independent of C infinity. Okay, dia tak kira banyak concentration at the infinity, but at C naught, kalau dia kata 4 saja, the concentration is 4, or the plot is only 4, so only 4 kalau put contohnya 4 house can be built at that plot. Okay, tak kira berapa banyak per maju of per mohon. Okay. Okay, so next is the Stern improvement of Gauss-Chapman theory. So the Gauss-Chapman theory breaks down with high charge density and strong field Okay, so high charge density, uh, the, let's say Ca2 plus, okay, and a strong beam. So if the membrane put in a particle field, okay, so uh, we cannot do the curve fitting using this equation. Okay, so with a surface potential of the order of 100 millivolt, so the expansion factor in equation 11.48 becomes E4 equal to 55. So if C infinity, the concentration at infinity is 0.1 mole, so the concentration at the attracted ion work out to be 5.5 m molar right at the surface. So a value above a saturation for many. Okay. So, too many ion at the membrane. Okay, so not all not all ion can uh, make interaction with the. Okay, and the theory has this Gauss-Chapman theory has a greater tendency to pair with multivalent ion, which interact more strongly with a charged surface and can even bind with a high degree of reactivity. Okay, so this one here you can see if we have Na plus, Ca2 plus. Okay, so Ca2 plus will interact more strongly with the charged surface, leaving Na plus hanging around in the solution. Okay, so that one will make, let's say, if Na plus is really needed in our body, but because of the Ca2 plus already taking the place, so we are going to miss the Na plus ion. So we have the Stern modification. So the Stern layer takes into account the finite size of an ion. So here, finite size of an ion. So the Na plus, how big is the ion, and Ca2 plus, how big the ion. So the closest it can get is one ionic radius away. So kalau kita ada gambar lagi senang. So satu the membrane and the ion. Okay, so the ion can uh, arrive at the membrane, touching the membrane with this the one this radius, it radius. Okay, so we have two layer, third layer. So third layer is the one that attached to the membrane, and diffuse layer is the next layer of the membrane. So exhibit surface binding to site on the membrane surface. To be in contact with the surface, they must be within one radius within then a position at x equal to a. Okay, so here we see that uh, these are the first layer and these are the second layer. Okay, the density of fixed chain charge in the membrane becomes from the Stern layer plus the diffuse layer. Okay, so using the kinetics, ion in the Stern layer are described by a binding equilibrium. For a cation A plus binding to a negative charge site S minus. So this membrane, we have a charge site S minus. So we have A plus plus S minus A S. Okay, so the concentration equal to this equation. So Ca, so concentration A plus at X equal to A. Okay, the binding energy, chemical part and electrolytic part, epsilon K equal to epsilon K naught plus E A to the Z by A. So K naught is the binding constant that will be seen in the absence of electrolytic reaction with the surface. Okay, so the charge density of the Stern layer depends on the density of the fixed charge that form the binding site, rho S, and the fraction of site occupied S minus NA. Okay. So kalau kita kalau macam tadi kita ada kata 4, kalau ni kata kita ada 10 site, binding site. Okay. So let's say 6 site dah di binding, ada 4 lagi site yang belum di bind oleh the ion. Okay. So the sigma T charge potential or charge density can be written as this equation for the Stern layer, and these are for the diffuse layer. Okay, so we can use this equation and some method or MATLAB. Okay, write this equation into the code, and we can find the charge density at the surface charge density of the membrane. Okay, so what are the difference between the Gauss-Chapman and Stern theory? Okay, so Gauss-Chapman only depend on charge. Different ion with the same charge will give the same result. Okay, so it doesn't care whether the charge, the ion is big or the ion is small. Okay. And the Stern, different ion will have different binding constant. Okay, not that this ion specific, depend on the radius of the ion. Okay, so what we want to say here is that in the our membrane there is uh, the binding site. Okay, so the ion can bind to that site. So how many ion can bind that site for a certain number of time for the surface charge density.